Hello everyone, welcome to my channel Essentials of Electronics. In the previous video, we discussed the types of biasing of BJT: base bias with emitter feedback, base bias with collector feedback, and emitter bias. In this video, we will discuss voltage divider bias, the comparison of different types of biasing we have done in BJT, and stability factor. I will try to draw a circuit for voltage divider bias. Identify the portion where the voltage is being divided in the biasing circuit which we are doing now. A normal BJT. I am drawing a resistor to the collector terminal. Let me name it first: collector, base, and emitter. Take a resistor and connect it to the emitter terminal. This is going to be RE. In order to have a voltage dividend, a simple potentiometric setup is connected to the base region. Now we have formed a voltage divider. This voltage divider section is connected to our transistor in this way, right? So let us name this as R1, R2, where R1, R2 will be behaving as the voltage divider resistors. Let me name the currents. The supply voltage is plus VCC, IC, and here a total current of I2 and IB flows in. This is I2 current. Here we have emitter current IE and the base current IB flowing into the base terminal. This is the circuit diagram for voltage divider bias. We will try to write equations for voltage divider bias. The potential at VB is now approximately equal to R2 divided by R1 plus R2. This part is the voltage divided part into the total supply voltage VCC. VE is equal to VB minus VBE. V is the emitter voltage. IC, the collector current, is approximately equal to IE, and IE is equal to VE divided by RE. The IE resistor, its value will be equal to the voltage drop at the emitter terminal divided by RE. Therefore, the VC value will be equal to VCC minus IC RC. Also, we have VCE is equal to VC minus VE, because the voltage drop across this VCE, the potential between this is VCE is equal to VC minus VE, and therefore VCE will be equal to VCC minus IC into RC plus RE. These are the related equations with respect to voltage divider bias. The basis for this is simple Kirchhoff's voltage law. Now we'll try to compare the base bias circuit. In base bias circuit, the Q point always value is approximately IC is equivalent current to the emitter current. IC is equal to beta into IC is equal to beta into VCC minus VBE divided by RB. In case of base bias, who is having the most stable? In emitter bias, IC is equal to VEE minus VBE divided by RE plus RB divided by beta, and in collector feedback bias, IC is equal to VCC minus VBE. This in collector feedback bias, VEE is replaced by VCC and RE is replaced by RC. In voltage divider bias, we have IC is equal to, just before we have written the equation, IC is equal to R2 divided by R1 plus R2 into VCC minus VBE divided by RE. So what is the meaning of stability factor? The process of making operating points independent of temperature changes or variations in the transistor parameters. That is beta depends on beta or the VBE value. That is known as stabilization. What are the factors that affect the stability of the operating point? The temperature dependence of IC, the change in VBE and beta due to the replacement of transistor. There is another component called thermal runaway. In case we are not designing the suitable values of RE, RC, then the value of IC will be more. As the current increases, the temperature will also increase and drastically lead to breakdown of the device. This concept is called thermal runaway. So it is desirable and necessary to keep IC constant in the face of variations of ICBO. Sometimes it is also represented as ICO, the saturation current. The stability factor S is given by the change in the collector current divided by the change in reverse saturation current at constant VE and beta. So it is very important to maintain the output current IC. Heat sinks. What is the need of heat sink? In the last slide, we discussed about thermal runaway. Thermal runaway is the concept of breakdown of the device due to increase in temperature. Why does the temperature increase? At certain faulty conditions, a collector current, probably the IC current may increase and hence leads to the increase in temperature. This leads to a condition called thermal runaway. In order to avoid this, heat sinks are provided along with the semiconductor devices. Heatsink is a mechanical device. It is connected to a power transistor in order to dissipate the heat generated. For example, I'll just draw a simple diagram of a heatsink. Let it be like this with a mounting surface. Where is it mounted? It is mounted to a junction in a case. This is called the junction and this is called the case. So we have a certain area far apart from this. Yes, we have a limitation so that there is possibility of air circulation and the temperature may cool down because of this. The heat flows through the heat sink and is radiated to the surrounding air. So when heat sinks are provided, what happens? The expression for stability factor in common emitter configuration, we'll be doing it now. IC is equal to beta IB plus beta plus 1 into reverse saturation current. Differentiating the above equation with respect to IC, then 1 is equal to beta into DIB divided by the differential. What is DIB? The differential change in the base current to the differential change in the collector current plus beta is the current gain. Beta plus 1 into the differential change in reverse saturation collector current divided by differential change in the collector current. It is also equal to, again simplifying it further, beta into DIB by DIC plus beta plus 1 divided by S, where S is equal to beta plus 1 divided by, I'm writing the denominator here because of lack of space, 1 minus beta into DIB divided by DIC. And when we are talking about the biasing, we must be clear on the operating points and the load lines. DC load line. What is DC load line? A line that is drawn with the values of VCC and IC. This is called DC load line. For example, when we are operating the transistor, the voltage drop across VCE, the points considered here are the different voltage operating points of VCE and the current. So the output parameters when it is acting as an amplifier, so at various points of IB, by keeping IB constant, IB will be in the range of microamperes. Like for example, for BC 107, BC 547, for such ratings, we can fix particular value of IB 100 microampere to a range of 250 microampere. And by assuming this IB initially 0 microamperes of current, the value will be very less. And after increasing the value of base current, a linear curve initially is formed, and the collector current remains constant with respect to various changes in the VC. This is for one particular value of base current. Again, if we change the value of base current, again initially we will be able to find a linear curve, and then at a particular constant IC, the VCE will be, though the voltage across the collector emitter changes, the collector current remains the same. And for another different value of IB3, we will be getting this kind of curve. For another value of base current, we will be getting this curve. And locate a point, maximum, a saturated point at IC and a saturated point at VCE. Try to draw a line connecting the maximum points of IC and VCE. Yes, and the line tries to meet the points at on the curves like this. These points are called the operating points, and the line such drawn is called the DC load line. So this maximum point achieved is called VCC point, and this value of IC is equal to VCC divided by RC, and this VCE will be approximately equal to the VCE. Thus, in this video, we have covered the voltage divider biasing, comparison of the different types of biasing of BJT, and the stability factor with the DC load line and operating point. Thank you.